Welcome to The Explainer. Today, we are diving headfirst into one of the most, and I mean most, mind-bending experiments in all of physics. We're talking about the delayed choice quantum eraser. So, get ready, because reality, it's about to get seriously weird.
All right, let's just jump right in with the big question. The one that sounds like it's straight out of science fiction. Can a choice you make right now actually change something that has already happened? I know, it sounds impossible, right? But this isn't just a fun riddle. It's a real question physicists have wrestled with for years. And believe me, the answer? It messes with everything we think we know about the past.
And look, this question didn't just come out of nowhere. It was dreamed up by the legendary physicist John Archibald Wheeler back in 1978. Now, this guy was one of the absolute giants of physics. He wasn't just asking, what if? He was designing a way to really poke and prod at the very fabric of reality, to see if he could push the bizarre rules of the quantum world right to their breaking point.
All right, first up, a paradox in time. So how on earth do you even begin to test an idea this wild? It all starts with a very strange concept, how the simple act of looking at something can apparently shape what it did in the past.
Okay, so the very first thing we have to get our heads around is something called wave-particle duality. Now, in our world, things are pretty simple, right? A baseball is a solid thing, a particle. A ripple in a pond is a wave. They're two different things. But down in the tiny quantum realm, particles, like photons, can be both at the exact same time. It's like they haven't made up their mind what they want to be.
And here's where it gets really important for our experiment. That little photon, it doesn't just pick whether it's going to be a particle or a wave. Nope. It kind of hangs out in this fuzzy, uncertain state of both until something or someone measures it. The very act of looking at it, of measuring it, is what forces it to, pick a side. It's the observation that locks in its reality.
So let's meet the quantum players. To really understand what's going on, we have to break down the building blocks of this whole experiment.
Now, the best way to see this in action is with the famous double-slit experiment. So imagine you're shooting photons one at a time at a wall with two little slits in it. If you just let them do their thing without watching, you get this beautiful striped pattern on the back wall, an interference pattern. That tells you the photons acted like waves, going through both slits at once. But the second you put a little detector there to see which slit each photon goes through, poof, the pattern vanishes. The photons start acting like tiny billiard balls, and you just get two clumps behind the slits. Just by looking, you change the outcome. Okay, as if that wasn't strange enough, this experiment adds another layer of quantum weirdness, entanglement. This is where you can link two particles, like twin photons. They become connected in this really deep way. So deep that if you measure one, you instantly know the state of the other one, even if it's on the other side of the universe. Einstein himself called it spooky action at a distance, and trust me, it is absolutely crucial for what comes next.
Okay, time for the main event, the delayed choice revealed. So what happens when you take that observer effect from the double-slit experiment and you mash it together with the spooky connection of entanglement? Well, you get to the very core of this whole thing. This is where we see it all come together.
Okay, this is it. This is the whole shebang. So we've got our two entangled twin photons. Let's call them photon A and photon B. Photon A is the one we send through the double slits. Its twin, photon B, travels a much longer path to a set of special detectors. Now here's the crazy part. If we measure photon B in a way that tells us which slit its twin, A, went through, photon A behaves like a particle, no interference pattern. But if we set up the detectors for photon B to erase that information, so it's impossible to know which path photon A took, its twin suddenly behaves like a wave, and that interference pattern comes right back.
But wait, here's the absolute kicker. The choice of how to measure photon B, whether we want to know the path or erase the path information, that choice is made long after photon A has already gone through the slits and hit the back wall. Let that sink in. A decision we make in the present seems to be reaching back in time and changing the physical reality of what its twin photon did in the past. It's just wild.
All right, let's talk about rewriting the rules of reality. Because, you see, a result like this isn't just some weird little thing that happens in a lab. It has huge philosophical fallout. It makes us question everything.
Yeah, this experiment really throws a wrench into our ideas about time. So there are two big ways people think about time. One is the A theory, the common sense idea that time flows like a river. The past is gone, the future isn't here yet, and only the present is real.
But this experiment really challenges that, because the past doesn't seem so fixed anymore, does it? Then there's the B theory, or the block universe idea. This says that the past, present, and future all exist at once, kind of like a map. Our experiment seems to fit a little better with this view, that our measurement in the present is just illuminating a part of the past that was always there, but was just fuzzy, undefined.
When you get right down to it, this one single experiment takes a sledgehammer to three of the biggest ideas we have about how the world works. First, causality. The idea that the cause has to come before the effect. This experiment puts a huge question mark on that. Second, non-locality. It proves that those spooky, instantaneous connections between particles are real. And third, realism. This is the big one. The idea that there's an objective reality out there that exists whether we're looking at it or not. This experiment suggests maybe not.
Okay, let's move on to fact versus science fiction, because before we all run off to build flux capacitors, it is super important to talk about what this experiment does not mean. There are a lot of misconceptions out there.
So let's be absolutely crystal clear about a few things. First, this does not let you send information back in time. You can't send lottery numbers to your past self, sorry. No laws of physics are being broken here. What we're seeing is a very, very weird quantum correlation, not backward causation. And maybe the most important part, you can't see the wave pattern just by looking at the data from photon A. It looks totally random. The pattern only appears after the fact, when you take the data from photon B and use it to sort through the results from A. It's about the relationship between the two, not about changing a single event.
And so, all of this leaves us with one last, really provocative question to chew on. If a choice we make now helps to define what actually happened back then, what does that say about reality itself? It suggests the past isn't some fixed story that's already been written. Maybe it's more like a story with a bunch of blank pages, and our observation, our measurement in the present, is the ink that finally fills them in. So the big question is, does reality just wait for us to look?